Hello everyone, we are going to look at today's AtCoder beginner contest. Since problem A and problem B are far too easy, we will not talk about them. Now let's start from problem C. So we have an infinite two-dimensional grid, and we want to go from R1C1 to R2C2. So we have three types of moves. We can either move along this diagonal, or we can move along the other diagonal. Also, we can move to neighboring cells. Here neighboring means distance, so it is Manhattan distance is no larger than 3. So we want to find the minimum number of moves needed to go to R2C2 from R1C1. We can see here that these numbers can be very large. So we cannot naively try every possible move. We need to find some pattern. So now let's first look at some examples. In the first example, we first move along this diagonal, then we use the neighbor. In the second example, we first move along this diagonal, then we move along this diagonal. And in the third example, we first move using neighbors, then we use this diagonal, then this diagonal. In the third example, R1 equals R2 and C1 equals C2, so we don't need any moves, and the answer is 0. So, is there any pattern? Let's start from the easiest case. So, in this problem, the easiest case will be like sample 4. That is R1 equals R2 and C1 equals C2. It means they are the same point. So this is the first case. The answer will be 0. So now let's find the second case. The second case is that we can move from R1C1 to R2C2 in one move. That is, either we have R1 plus R2, R1 plus C1 equals R2 plus C2, or R1 minus C1 equals R2 minus C2. These are the two types of diagonals. Then we have the case that they are neighbors. Then we have this third case. In the third case, we will use two types of moves. It means either we will move from one diagonal, then use the other diagonal, or we will move using neighbors, then using diagonal. So let's first look at the case that we use two diagonals. We must have a middle point. Suppose it is PQ. Then we will have, suppose that R1 plus C1 equals P plus Q, and R2 minus C2 equals P minus Q. Then this is a pair of equations, so we can solve the equations, and we will have 2P equals R1 plus C1 plus R2 minus C2. So we know that P is an integer, so that means R1 plus C1 plus R2 minus C2 must be even. It cannot be odd. Otherwise, these equations do not have integer solutions. The other case is just the same, that is, we will swap them to get R1 minus C1 equals P minus Q, and R2 plus C2 equals P plus Q. They are the same because we can swap R1 C1 and R2 C2, since we can either go from A to B or go from B to A. They are equivalent. So in this case, we need to check whether the parity of R1 plus C1 plus R2 minus C2 is valid. Then we have the fourth case. We will first move to a neighbor cell. Then we will check whether we can move one step from the neighbor point to the target point. So in this case, we will enumerate all possible neighbors. That is, we will enumerate from R1 minus 3, R1 plus 3, and C1 minus 3, C1 plus 3. We will enumerate all these points, and of course there are some invalid points whose distance from R1 C1 is larger than 3, and we will exclude them. For the valid points, that's P prime, Q prime, we will use it as a new middle point, and we will check, just like in the second case, whether we can go from P prime, Q prime to R2, C2. And finally, we have the fifth case. It means we cannot find a middle point PQ, and we can neither find a middle point P prime, Q prime. So here I will first claim that the answer to the fifth case will always be 3. Why? Because we cannot find the middle point PQ in the third case only if the parity does not satisfy our conditions. But we can always move to a neighbor point to change the parity of R1, C1, R2 minus C2. Then we can use the way we used in the third case and go to R2, C2 within 2 steps. So the total steps will be 3. So now we have all the cases listed and we can have this problem solved. The code is just like what has been said just now. Okay, now let's move on to the next question. Problem D, increment of coins. So we have a bag containing A, gold coins, B, silver coins, and C, bronze coins. In each time we randomly take out 1 coin from the bag and put back into the bag 2 coins of the same kind as the removed coin. So suppose we have A, B, C right now. Then after we pick 1 coin and put back 2 coins, the case will come to A plus 1, B, C, or A, B plus 1, C, or A, B, C plus 1. So when the bag contains 100 coins of the same color, we will stop. So that means whenever one of these 3 numbers come to 100, we will stop the iteration. So this problem is a typical depth first search problem, since here we have upper limit of 100. So there are at most 1 million. So there are at most 1 million situations. So this can be solved easily through some memoization. Let's just look at the code. So here we have a memo to memorize all the conditions that we have met. We will start from the original set, but before that we will sort the coins first, since it doesn't matter which type of coin we have. We just have 3 types of coins. Then we come into the depth first search. So we first have 2 exit conditions. The first is that we have only 1 type of coins in the bag. Then we can directly return the answer, since each time we can only pick 1 type of coin. The second exit is that 1 type of coin has reached 100. Then we need to stop. And here, if we have met this situation before and we have memorized that, we will just return it. So in other cases, we will enumerate which type of coin we have picked from the bag. and we will change the setting according to the type of coin we have picked out. Then we will add up the expectation. So here we use the addition of expectation. So suppose that we are at a situation S, and we can go to S1, S2, and S3 in the next step. And for each transition, the probability is P1, P2, and P3. Then the expectation of S can be described as the sum of the expectations of S1, S2, and S3 times their probability. That is, the expectation of S is 1 plus sum Pi times E expectation of Si. So here we add 1 because in this turn we picked out one coin. So we will add 1 to the sum of this. Okay, that's all for problem D, and now we will go to problem E, Third Avenue. So here we are met up with a very familiar problem. We have a two-dimensional grid with H horizontal rows and W vertical columns. So we have a starting point S and an end point G. And empty cells are dots, and we have walls which we cannot cross. And one more thing is that we have teleports. They are lowercase English characters. So that means if there are A1, A2, A3, and AK, we can just in one step go from A1 to A2, or A1 to A3, or A1 to A4. So first, suppose that there are no teleports in this problem. Then obviously we can use breadth first search to solve this problem. In each turn, we just try all the 4 possible directions. We will use a Boolean array to mark whether a cell has been visited or not. But how do we take into account the teleports? So there can be many cells with the same character. We might have 1 million A's, 1 million B's. So if we just naively implement the algorithm, so besides the 4 possible directions, we will try to, for example, if we are at A right now, we will try all the other A's. For most of them, we will not actually go to them because most of them might have been visited. But we have to enumerate all the possible paths. So suppose that if we have 1 million A's, which is absolutely possible because H can be 2000 and W can be 2000, and in that case there will be 4 million cells in total. So if we have 1 million A's, for each A we will enumerate all the other A's. So we will have 1 million times 1 million, that is 1 trillion, which will lead to time limit exceeded. How do we optimize? Actually, we should observe that each type of teleport, that means each lowercase character, can only be used once during our breadth-first search. Why? Because when we first used the teleport, we are at a cell whose letter is A, and suppose we take D steps to go from S to A. Then here we will use the teleport, and we will go from this A to other A's. So this is the first time we use the teleport A. And the minimum steps we can get here is D plus 1. But due to the property of breadth-first search, if we try to use teleport A again, so say we are at A prime, and now we used D prime steps to get to A prime. Obviously, we will have D prime is larger than D, so the new value will be at least D prime plus 1, which will be less optimized than D plus 1. So we will not use teleport A again. This is the same case for other teleports. Teleport B, teleport C, teleport D, they are all the same. We will use them at most once. So with this optimization, let's see the code. We will use a teleport only if this type of teleport has never been used before. So with this optimization, we will get a total time complexity of n times h times w, which is acceptable. Now let's go to the final problem. Problem F, programming contest. So the description is simple and direct. So someone will participate in a contest, and the contest lasts for 10 minutes, and there are n problems. So each problem will take AI minutes. Then we need to make a choice. We need to choose from the n problems so that these problems take no longer than 10 minutes. And we want to find the longest possible time. So here we notice that the maximum n will be 40. So if we naively enumerate all possible subsets of problems, we will have 40/2 different subsets, and there are too many. What we will do, actually this problem is a very typical problem which will use the technique called meet in the middle. So what is meeting the middle? So this technique is usually employed in problems like this. That is, we have a big set which we cannot afford to enumerate all possible subsets. So here we have 40/2 subsets in the worst case. Then how will we implement meeting the middle? We will just split the original set into two halves. So now say n equals 40. We will make the problems 1 to 20 the first subset, say set L, and the problems 21 to 40, we will put them in the set R. So for each half, we just do naive enumeration. So now we will have 20/2 subsets for L, and also 20/2 subsets for R. Then we will enumerate the items in L, say Li. We will try to find the largest Ri in R, such that Li plus Ri does not exceed T. So this can be done via set in C++. We can quickly find the maximum number of Ri with the lower bound method of set. So actually this problem is not very difficult if you know the technique of meeting the middle. The code is easy. We just generate L, generate R, then finally we try to merge L and R. We enumerate Li from L, and we try to find the suitable Ri using the lower bound method of set, and update our answer. That's all for today's problems. Thanks for your watching. See you next time.